கொடுத்து சாருக்கு ஷேர் பண்ணி அவர் ஃபார்வர்ட் பண்ணிப்பாரு. காப்பி லிங்க்
ஷேர் பண்ணுறேன்
எனக்கு
சார். நீங்கள் கொஞ்சம் போவே கூடாது.
என் சேனலில் போகக்கூடாது.
ஆமாம் சார், ஏன்னா இந்த சேனலில் தான் லைவ் ஓடிட்டு.
சரி, ஓகே.
ஒரு லைவ் வந்துச்சு.
ஓகே, இப்போ எனக்கு ஷேர் பண்ணுறேன்.
நான் உங்களுக்கு ஷேர் நான் என்னிலேருந்து ஷேர் பண்ணேன். வாய்ஸ் மட்டும் கேட்குறேன் செக் பண்ணுங்க. அவ்வளோதான்.
A pleasant morning, one and all present here for Nano Chata 2026. Aringaranna Government Arts College, Villupuram is a prestigious institution of higher education established on 4 July 1968 by the Government of Tamil Nadu. The college offers a wide range of undergraduate, postgraduate, MPhil and PhD programs in arts, science and commerce. About the physics department. The Department of Physics was established in the year 1979 with BSc Physics offered in both English and Tamil medium. In the year 1998, it is elevated to PG department offering MSc Physics. In 2009, research activities commenced and scholars on both full-time and part-time research activities included for PhD degree. It is my privilege to welcome you all today's event on Nano Chata. On behalf of the organizing committee, I extend a warm welcome to our respected chief guests, distinguished speakers, faculty members, research scholars, students, and all the participants. The lab with an art, a virtual and discipline. I respectfully invite our honorable principal, Dr. A.S. Kumar sir, our honorable. I respectfully invite our. I respectfully invite our honorable principal. Lighting the lamp is an art, a virtual and discipline. I respectfully invite our honorable principal, Dr. A.S. Kumar sir, our honorable chief guest, Dr. Geeta G. Nair, distinguished scientist, Sixth Bengaluru, Dr. A. Sadiq sir, and also I invite our art principal, Dr. A.
ஃபோனில் எடுங்க சார்.
Dr. A. Samal Kumar sir and Dr. D. Manikandan sir to light the ceremonial lamp.
Good morning to one and all. A warm welcome to Dr. G. Geeta Nair, scientist at Bengaluru, and their team. Welcome, ma'am. And it's my pleasure to warmly welcome Mr. J. Manikandan sir, Managing Director and team. Welcome, sir. And I extend my welcome to our Principal, Dr. Satish Kumar, sir. Welcome, sir. And especially welcome to our HOD of Physics, Dr. Venkatesan, sir. Welcome, sir. And our department senior professor, Dr. Sambaj Kumar, sir. Welcome, sir. And Dr. Sivaraman, sir. Dr. Karthikeyan, sir. And all other teaching and non-teaching staffs of our physics department. I extend my cordial welcome to students and faculty members from various colleges participating in this event. This is the first time in our college history in hosting such a unique event, bringing together our renowned scientists from esteemed institution and to handle experimental demonstration like wind turbine demonstration, as you can see here. We proudly happy. Our sincere thanks to all the college students, those who have come here to participate in this Nano Jatra 2026 event. I welcome all the college students, those who have participated, and their staffs. Thank you so much. With your presence, this event has become successful. Thank you all. And I take this opportunity to welcome and thank Mr. G. Pandian, sir, Chief Technical Officer, SPT Chennai, who has arranged windmill turbine. And I personally thank SENS Bangalore Director and my senior Agapan, sir. They are not here, but I extend my thanks to them. Actually, நம்ம கல்லூரியில பாத்தீங்கன்னா 2016 we conducted national conference the first time in our department since 1979. After 10 years, after conducting various international national conferences in the history of our, this is the first time you are conducting an event, Nano Jatra event. That too, it's very special. இப்போ பார்த்தீங்கன்னா இந்த ஈவெண்ட் வந்து வேரியஸ் பார்ட்ஸ் ஆஃப் அவர் கண்ட்ரி நடந்துட்டு இருக்கு. அது நம்ம ஊரில் நடக்கிறதுக்கு சென்ஸ் பெங்களூர் ஹஸ் given the opportunity. So I would like to personally thank their team and also I personally thank those who are not able to come watching in the live in YouTube. And once again, I welcome you all for this event, Nano Jatra 2021. Jai Hind.
Thank you, sir, for your welcome address. Honor is the reward of virtue. It is now time to express your heartfelt gratitude and respect to our esteemed chief guest for graciously accepting our invitation and being with us today. May I kindly invite our respected principal, Dr. K.S. Satish Kumar, sir, to honor our chief guest, Dr. Geeta G. Noyer, distinguished scientist, with a shawl and memento as a token of our love, respect and appreciation. Thank you, sir. Invite Dr. A. Venkatesan, sir, head of the physics department, to honor our principal, Dr. K. Satish Kumar, sir, with a shawl and memento. Thank you, sir. I kindly invite Dr. A. Pradeep, Associate Professor, to honor Mr. Manikandan Jagadishan, Managing Director, Sunbright Tools, Chennai, who leads business operations and project executions with a focus on wind, solar, hybrid power generation technologies. Thank you, sir. Thank you. It is now my privilege to invite the President of today's function to deliver the presidential address. May I respectfully invite our Executive Principal, Dr. K. S. Satish Kumar, President of today's function, to address the gathering.
Respected colleagues, respected guests, dear students and business scholars, it's my pleasure to welcome you all to Nano Jata 2026 organized here at Harijarana Government Arts College, Villupuram. Today marks a significant step in our collective journey towards advancing scientific awareness and innovation in nanotechnology. Nanoscience and the nanotechnology are not merely emerging fields. They hold the power to redefine the future of energy, medicine, materials, and sustainable development. This event has been carefully designed to ignite curiosity and foster collaboration. The expert lectures will provide deep insights into cutting-edge research, while the live demo from nano experiments to wind turbine models will build the theory in practice. This quiz competition will challenge our young minds to think critically, and the prizes will serve as recognition of their talent and dedication. Proud to note that Nano Jata 2026 is not only an academic gathering but also a celebration of innovation and teamwork. The provision of free registration, lunch, and event kits reflects our institution's commitment. Dear students and scholars, I urge you to seize this opportunity, ask your questions, share ideas, and let this event be catalyst for our future endeavors in science. On behalf of this college, I extend my heartfelt gratitude to the organizing committee, especially Dr. A. Pradeep and the Department of Physics for their tireless efforts in bringing the vision to life. I also thank our faculty members and the supporting staff for the dedication in ensuring the success of this program. Let us together make the Nano Jata 2026 a milestone in our academic journey. With your enthusiastic gathering, I am confident that this event will inspire new ideas, collaborations, and innovations that will resonate for beyond these walls. Thank you. I wish the program may end. Thank you.
Thank you, sir, for your valuable message. An inaugural address sets the tone for the event, inspiring us with purpose and vision. It is now my privilege to invite Dr. K. Sambat Kumar, Associate Professor, to deliver the inaugural address.
Sir. Sir.
Hello.
thanks to all the participants who are participated in this event, especially from the other colleges throughout Tamil Nadu. I wish success for the coordinator as well as all staff members. Thank you.
Thank you, sir. It is now my great pleasure to invite Dr. A. Venkateshan, Head of the Physics Department, to deliver the felicitation address.
Very good morning to honorable members here. I would thank all the department staff members. First, I would like to thank our head man and the manager, principal, which all our health department, university sir, and our department staff, our department students, other department staff. So it is a very pleasure to thank our coordinator because it is a wonderful opportunity our college and department because it's a annual star 2026. It's very helpful to our students and existing scholars and other debating scholars and other faculty members also. Once again, thank our 82nd students. Thank you. Thank you.
Thank you very much, sir, for a thoughtful and inspiring felicitation address. Your encouraging words and valuable insights have greatly enriched this gathering. We sincerely appreciate your presence and time you have shared with us. Thank you once again.
So, I welcome our chief guest, J. Manigan sir, to share his view. Welcome, sir.
Hi everyone, respected professors and my dear students, warm welcome to you all. Let me introduce myself, and my name is Mani. I come from Sunrise to Chennai. Basically, we are in mechanical engineering and we are a OE vendor for Renault Nissan and Ichapam, Yamaha Motors and Kia Motors. Later we focus on the wind energy. So power is the most important for us. So we focus on the wind energy. So we taken further this wind, solar, hybrid power generation systems. So anyone know about the solar from here? Any student? Solar, we can installation means it will generate the power on the daytime only. But we go for in our system, in night time also it can generate the power. So in solar, it will be generate the power on the daytime in sunlight, and in wind, it will be generate the power on the night time. So we get the more energy from us. இப்போ தமிழ்ல பேசலாம் நினைக்கிறேன். So இங்க யாருக்கான சோலார் அந்த மாதிரி விண்ட் அப்படிங்கிறது இந்த ப்ரோசஸ் யாரா இருக்கீங்களா? Any questions about that?
Not audible, sir.
Sorry?
Not audible, sir.
Not audible. Okay, anyone have a question? யாருக்கா சோலார் பத்தி என்ன தெரியுமா? நீங்க இப்ப என்ன கட்டத்துல வந்திருக்கீங்க அப்படின்னு Okay, thank you very much for this wonderful opportunity to give us this connector, and thank you.
Thank Geeta G. Nair, Distinguished Scientist since Bengaluru, to address about the Nano Journal 2026.
Good morning, everybody. I don't have to say much. Straight away, I would like to start the program and give my lecture. So I hope you will be able to, keep silence for an hour and listen to what I have to tell. Thank you very much.
Thank you, ma'am. Every successful event is the result of collective effort, dedication, and enthusiastic participation. We are truly grateful to our esteemed chief guests, distinguished dignitaries, faculty members, participants, research scholars, students, organizing committee, volunteers, and everyone who contributed to the success of this program. We sincerely thank all our guests, speakers, participants, and volunteers for making this event a grand success. Thank you. Have a pleasant day. I kindly invite our honorable chief guest, Dr. Geeta G. Nair, to address a PhD 1993 in physics from Raman Research Institute, RRI, Bengaluru. She was a postdoctoral fellow at RRI and a visiting scientist at Kent State University, USA. Research areas of interest: liquid crystal gels and composites, nano-soft composites, soft anisotropic metamaterials, soft photonic systems,
டாக் எடுக்கணும் மட்டும் ஃபிக்ஸ் பண்ணு. மற்ற நேரத்தில் மூவிங்கில் வச்சு இப்போ டாக் எடுக்கும்போது அவங்க தான் இருப்பாங்க. அது மட்டும் ஃபிக்ஸ்டாக இருக்கும். ஹெல்ப் இருக்கேன். அப்போ இது கட் பண்ணிவிடு. இது வந்து ஒரு வீடியோவாக இருக்கும். இனாகரேஷனுக்கு ஒரு வீடியோவாக இருக்கும்.
கட் பண்ணி போட்ட குவாலிட்டி கம்மியாக குவாலிட்டி
எல்லாம் மேடம் முடிஞ்சவொடனே கட் பண்ணிக்கலாம்.
ஓகே.
Good morning, everybody. Can you all hear? Even at the last row. Can you hear me? Louder, please. Shall we start? I want everybody to just sit down and be quiet. If you are quiet, then we can hear actually. Whatever I speak, as well as if you want to ask something, we can hear. Otherwise, we won't be. Okay? Thank you very much. So, good morning. I still see some people standing. Can you please sit down? You can do that later. You can do that later. Please sit down. Thank you so much. And please put your mobile phones inside. Thank you. So, good morning everybody. I am very pleased to be here with all of you as part of this event called Nano Jata. Okay, the year is 2026. It's a series of event, okay, preceding a mega event called Bengaluru India Nano that's going to be held in Bengaluru in the first week of August. Okay, so this is one such event that is happening here. Such events are happening all over the country. Right now, another event is happening in Kannur, that is in Kerala. So this event is happening everywhere. I'll tell you a little more on that. What is the origin of this event in the coming slides? Okay. Okay, so I am Geeta Nair from Center for Nano and Soft Matter Sciences, and the title of my talk is Nature Inspired Structures. You will see in nature how nanostructures are formed and what is that speciality about these nanostructures, how it is helping the living beings, different types of living beings in nature, how it is helping. That is what I am going to talk about. Okay? So, next slide please. Before I go to the talk, I would like to acknowledge, thank the organizers from Anna University, Villupuram, Dr. Pradeep and his team, and Principal Dr. K. Kanagasavati, and all other volunteers, because I don't know their names, obviously, so I want to thank all of you for making this. I that is the main organizer, Dr. Subhash, from Center for Nano and Software Sciences and his team, and also my students from the center, Kavya and Deepak, for helping with the experimental, demonstrations, which they actually taught yesterday to the students from here. Some of the volunteers from here, they taught how to run the experiment, and the rest of you will see those demonstrations in the afternoon. So I thank them wholeheartedly. And I also thank the case, that's the previous slide please. Don't change the slide until I tell. Karnataka Science and Technology Promotion Society, it's called K-Steps. They are the ones who provided the money, the funding for conducting this event. So I thank them as well. So having said this, let me now start the main presentation. Go to the next slide please. So how many of you know what is a nanometer? Many of you are MSc students. So do you know what is a nanometer? If anybody wants to answer or want to ask a question, that person should raise their hand. If anybody knows the answer, they can raise the hand. Okay, please. Yeah. No, what is a nanometer? 1 to 100 nanometer is different. You know what is 1 centimeter, right? So nanometer, if you want to say, okay, in terms of centimeter, how much that would be? Yes? Okay, 10 to the power of minus 9, what? My 9 is what? Meter. Centimeter or meter? Meter, correct. So that's what is 1 nanometer. So can you see a nanometer sized object? Something that is 10 to the power of minus 9 meter, will you be able to see? No, right? Okay, let us see how we can see these things, what is their properties, what is that you see in the nature. Let's go ahead with the talk. So go to the next. So this is a normal scale, using which you can measure centimeters and inches and so on, right? So I just want to, whatever he said, I don't know his name, go to the next one. So 1 centimeter is 1 followed by 6 zeros nanometer, and 1 meter, 1 meter is 1 followed by 9 zeros nanometer. In other words, 1 nanometer is 10 to the power of minus 7 centimeter or 10 to the power of minus 9 meter. Okay? And nanometers are usually denoted as nm. It's written as nm. Like centimeter we write cm. Similarly for nanometer, it is denoted as nm. Next slide. So just to give you an idea about what is this nanometer, how you can imagine that, what, when you think about nanometer, what, imagine, when you talk about inch, you will approximately know what is the length. But when you think about, you won't be able to think, right? It's not as easy as thinking in terms of centimeter or inch. So just to give a perspective on that, go to the next. So if you look at atom, it is about 0.1 nanometer. And if you see a DNA double helix, nanometer in diameter. And a typical protein is about 10 nanometer in length. Computer transistor these days, they are 100 to 200 nanometer. A human hair which you can touch, correct, you can feel, and that one is about 100,000 nanometer. In nanometer, 100,000. So coming to a small tiny mites, dust mites, it's about 200,000 nanometer. And go to the next one. An ant, which you can see, it's about 5 mm, which means it is 5 million nanometer. nanometer. It's very difficult, hard to imagine that, right? And humans, we are all about 2 meters tall. So in nanometer, we are nanometer tall. And the Empire State Building, okay, in New York, recently was famous for some incident. I don't know, you might have read somewhere or seen somewhere. But anyway, let me know. That is about 381 meters tall, which means it is 381,000 million nanometers. So that's the kind of mind-boggling numbers you will get if you think or to measure objects that are seen with our eyes. Okay? So, now, you also must have heard about nanoscience and nanotechnology. Many times what people do is they interchangeably use these two terminologies. But you should know what is actually nanoscience and what is nanotechnology. Nanoscience is the study of structures or materials in the range of 1 to 100 nanometer. Somebody said that 1 to 100 nanometer or something. But that is the range. The range of materials or objects or anything that is in this range, if you study for its properties and measure its properties, then all that comes under nanoscience. So what is nanotechnology? Nanotechnology is a tool that helps examine this material at the scale, nanoscale, and also use these nanomaterials, using this, the devices that you can make, okay? So the technology involved in making devices using the nanomaterials is known as the nanotechnology. So, in other words, nanoscience answers the question, what happens at nanoscale? And nanotechnology answers the question, how can we use the knowledge of nanoscience to make devices, products, anything, and improve our lives. That is what is all about nanoscience and nanotechnology. Now, going back, some kind of history of nanoscience. Although this field is relatively a new field actually, but all about, don't go until I think. Okay, so the history of nanoscience dates back to 1856, when Michael Faraday actually did some experiments or using some gold. Actually, he was trying to make very thin foil of gold for his experiments, nothing to do with the nanoscience. While he was doing this experiment, he was going on washing this, the gold sheet or the film, so that he makes it thinner and thinner. And whenever he washed this gold foil, he collected that liquid, water actually, he was washing it into the water. He collected that in a beaker, and he found that the solution in the beaker is ruby red in color. Usually, what is the color of gold? What is the color of gold? Do you hear the bag or not? Can you? Hello? Hello? Hello, in the bag. Do you hear? Okay, then what is the color of gold? Huh? You don't know what? Nobody is wearing a gold ornament here? Yeah. Yellow. So, he expected that the solution to have a yellow color. But instead, he found that it is red in color. Should I come to the back side? Should I just walk up and down so that they can? Otherwise, so what was I saying? Somebody repeat. I'm a little scared about walking here. So what was I saying? Can you repeat? You heard that. Okay. So Michael Faraday, when he did the experiment, as I was telling, he was collecting the liquid in a beaker and he found that it is ruby red in color and not yellow. That was a surprising thing for him. And then what he did was, he shined a light through that liquid. And he saw that there is a perfectly defined cone of light passing through that liquid, which means that there are particles in that liquid. At that time, we did not know that this liquid contained gold nanoparticles. Now we know that we can actually get gold nanoparticles when it is dispersed in water. It shows ruby red color, and you will find this demonstration is there in the afternoon. The students are going to demonstrate these things to you. Okay? Yeah. Next. So about a century later, another great scientist called Professor Richard Feynman. I don't know how many of you have heard about him. Have you? Can you tell something about him? Yeah. Yeah, he did a very famous lecture series. Like she said, he is known as father of nanotechnology. Can you tell?
Richard Feynman இருக்கு எல்லாரும் நானோ சயின்ஸ் அண்ட் நானோ ஃபர்ஸ்ட் பர்சன் அவங்க தான் நானோ டெக்னாலஜிங்கிறாங்க ஃபர்ஸ்ட் பர்சன் வந்து.
That's fine. So what he said was, in one of his famous lecture series, he said, there is plenty of room at the bottom. By that, what he meant was, go down. So he said, up to now, we have been looking at things by taking, bulk materials, which we find in the earth, the minerals and all that we study, all of them are bulk. But he said, ultimately, in the great future, we can arrange the atoms the way we want. Okay, he said that. So his prediction has come true now. So there are now nanotechnology that realized small, devices at the nano scale. You can actually deliver drugs using such tiny devices. You can also find, the transistors in computer chips have come down to nanometer scale. All these things are being realized and still continue. So whatever we predicted at that time has come. So the next slide, please. We also have a great scientist among us in our country, Professor C.N.R. Rao. Many of you must have heard about him. He is the pioneer of nanoscience and nanotechnology in our country. In fact, he is the one who is responsible for putting together this Bangalore India Nano event and the Nano Charter. He wanted the scientists who practice nanoscience and technology to go all over the country, reach students like you, talk to you, and impart the knowledge and make you curious about this field of science, this technology, so that you can actually learn and come up with newer and newer products. That was his idea. With the help of case steps, he put together this program. So we must all thank him for this action. So the next slide. So having said this, you have any idea how we can see these nanostructures or nanomaterials? Microscope. Which microscope? Why is that?
This is just the height. It doesn't want to see the height or even a small tiny particles.
So what does it use?
What?
What does it use?
seeing a very micro.
Yeah, what is the principle? So he has said, what he said is right. There are electron microscopes. It is possible to, examine the nanomaterials or nanostructures using electron microscopes. And unlike the optical microscope, you are all familiar with the optical microscope, no? Yes.
Yes, of course, we are told.
Yes. So you know optical. What does an optical microscope use? Oh, I'm sorry, I can't. So does anybody know what an optical microscope uses? To view the things? Okay, so an optical microscope uses light, visible light, correct? Visible light which has the wavelength range anywhere from roughly 400 nanometers to about 800 nanometers is wavelength. So because of that we can magnify objects that are in the microns range, what we can't see. But if you are going to a nanometer scale, that's the optical microscope. Go to the next one. So in an electron microscope, instead of light, focused electrons, focused beam of electrons are used to view the nanomaterials. That is the difference. And it is a very sophisticated instrument and not very easy to put together, unlike the optical microscope. So the scientists have developed this kind of microscope just to view the nanostructures. This is the one known as scanning electron microscope. So it can actually examine the surface of nanomaterials. The next one, go to the next slide. So the next slide shows the transmission electron microscope. Using this, you can go deeper inside a nanostructure, deeper, and check the structure inside any of these objects or materials. So now, next slide. Coming to the actual topic of the presentation, what you should know is nature has been designing nanostructures for millions of years. Many plants, insects, bacteria, birds, and animals possess natural nanostructures. They occur naturally, and such structures enable them to have very special abilities, as you will see. Next slide. So first one I am going to talk about is the bacteria, the tiniest of the living beings, the tiniest of the tiniest. So this one is called magnetotactic bacteria, and they live in fresh water as well as in salt water. But one condition has to be met. They live in a kind of a zone where the oxygen-rich water meets the oxygen-deficient water. So that zone is called oxic-anoxic transition zone. That is where they live and grow and thrive. So such bacteria, they produce very, very tiny iron particles. These are iron oxide nanoparticles inside their cells. And these iron oxide nanoparticles form a chain. Okay, you can see the cartoon there. Yeah, you can. So this is the cartoon of this magnetotactic bacteria. You can see that those particles are lined up here. And they are typically covered with the protein layer. And this is known as a magnetosome. That's the name. And this bacteria has a tail also. It's called flagellum. Using this flagellum, they actually swim in the water. So when scientists actually observed this bacteria under a transmission electron microscope, they observed the same thing. You see that it's lined up, all the particles are lined up, and this is the one which is called as the magnetosome. This is at a higher magnification, you can see it very clearly. And this magnetosome is like a compass, and using this tiny nano compass, excuse me, hello, whoever is serving tea, hello, you are not supposed to serve the tea in the middle of the talk. Have tea later. Are you a student? Are you a student? Then you have to sit. The tea is for outside. You can all have tea and snack or whatever it is after the lecture, not during the lecture. So, I said that this magnetosome acts like a nano compass, and it aligns along the Earth's magnetic field, and using this tail, the bacteria can swim towards the region where the oxygen rich region meets the oxygen deficient region, the OATZ. Okay? So that is what the nano compass. Nature has provided the bacteria with this nano compass so that it can grow, thrive, and live in a region that it wants to live. Okay? So that is the nature's beauty. Go to the next slide. So using this, this phenomenon, the scientists actually got inspired by this, and they have produced different types of nanoparticles, iron nanoparticles, especially for drug delivery. Let's say a patient has a tumor, okay? A patient has a tumor. You can deliver the drugs or medicine exactly to the tumor using this technique. You have these nanoparticles, and then these are magnetic nanoparticles. By applying an external magnetic field, you can guide the drug to the tumor, and the patient can be cured without any of his cells being destroyed, healthy cells being destroyed. Only the tumor cells gets destroyed. So that is the technology the scientists have been able to develop using this, the technology that is given to us by nature. That's the first example. Go to the next slide. Okay, these are called as diatoms. These are single cell microalgae. Yeah, single cell microalgae. They live in, again, deep inside water. Fresh water or salt water. They live in deep inside. Go to the next one. So they generate about 20 to 50% of oxygen produced on the planet each year via photosynthesis in a region where there is hardly any light. Have you heard of photosynthesis is being done in dim light? You need lot of sunlight, correct? But this organism can do photosynthesis with even very little light. So the inspiration, that's because they have a kind of a shell around them known as crustule. Go to the next slide. And these crustules have nanostructures in them. Okay? And using this, they are able to do the conversion of light energy. How much are a small light, little light? They are able to convert that into chemical energy and do the photosynthesis. Next slide. So this is an inspiration was to produce solar cells even with very little light. You know that the solar cells don't work when there is no sunlight. On a cloudy day, the efficiency is very, very poor. So now you can think of producing solar cells using this technology, the diatomist forces. Next slide. Have you heard of geckos? Geckos are lizards, garden lizards. I'm sure you know garden lizards. There is one called poke gecko, and these actually can climb up the wall or they can run across the ceiling at lightning speed. They don't fall. That is because they have very special toes. Very special toes they have, and these toes contain nanostructures, and these nanostructures, in that scale, they produce electrostatic forces, van der Waals forces. You must have heard about it. Because of these van der Waals forces, these nanostructures, they act like adhesives. There is no any type of no, it's not like a sticky tape where you have some material on it to stick. No, it is only the electrostatic force that is responsible for this. Special type of toes they have, using which they get stuck on the wall. Next slide. So that's the nanostructure. Okay. The next slide. Okay, using this gecko-inspired nanotechnology, there are companies that have now producing adhesives. These adhesives they can use to hold objects. I will show you the video in a minute. Stanford University, Stanford in the USA, they have made robots. They are called sticky robots that can climb the walls. On the vertical wall, they can climb easily. They have made these robots. Now, using these robots, now they are using these robots in space to collect garbage. There are a lot of garbage in the space. I don't know how many of you are aware. Whenever we put satellites there or whenever we put something there, some things don't work and they just keep orbiting over there. They are all occupying the space now. Humans are actually throwing garbage even into the space. So these sticky robots are being used to collect these garbages. So that's the kind of progress, all thanks to Gecko's toes. Okay, go to the next one. Can you play the video? Just be silent and watch the video. You don't need any audio for it, but just watch. So this company has made this, you can see those tapes. Okay, they are working only on the principle of Gecko's feet. That is, it's only the electrostatic, van der Waals forces. Sticky substance on the tape. Can you play this video? No. Can you play that previous video? Doesn't work. I think that video is not going to work. I'm sorry. Maybe the next one. Yeah. Next comes the butterfly. You all know butterflies, they are beautiful. They have beautiful wings, colored wings. Okay. So now the color of these wings comes from where? Any idea why the butterfly wings have colors? Any idea? Okay, definitely it is not because of any dyes or paint or anything. It's not because of that. It is because of some kind of a nanostructures present in these wings. And the color that is produced out of that is known as structural colors, not paint or dye, pigment, no. Okay? So these are structural colors. That is because they have a certain nanostructure and they behave like photonic crystals. What are photonic crystals? Photonic crystals are materials which have a periodic arrangement of materials kept side by side. One part of it is a high refractive index, next part is low refractive index, high, low, it goes, and there is a periodic variation in this refractive index, and because of that, and the periodicity of this structure is 100 to 200, a few hundred nanometers. That is the nanostructure, and because of that, no, don't go back. Because of that, when ordinary light, even the light outside, and that is what is the. So when the light falls on this butterfly's wings, some colors get reflected back. They do not penetrate the wing. They get reflected back. Some will go through, but some reflects. So whatever is reflected color is what you are seeing. So they are not pink. They are because of Bragg refraction. Some of you must have learned about Bragg refraction. So it is because of Bragg refraction. Next slide. So this is when you put the butterfly wings under a transmission. Let's say first you put it under the optical microscope, you see the color. When you put it under a microscope, you see those periodic structures, and further you increase the magnification using the transmission electron microscope. You see the nanostructures coming out. Next slide. So using this as an inspiration, okay, using this as an inspiration, there is a company called Meta Materials Inc., a Canadian company. They developed a technology of making, okay, notes, currency notes. They made currency notes that reflect a single color. Why did they do that? You know that currency notes can be easily faked. Fake currency notes are printed easily, right? Whereas, if you do this kind of currency notes where such nanostructures are imprinted, then it is not easy to fake them because these are very sophisticated technology that is being used. So, there is already an application for this type of, nature-inspired nanotechnology. Next slide. I don't think many of you would have heard this name, Edelweiss. It's a name of a flower. Edelweiss is the name of a flower. These flowers grow on the Alpine mountains in Europe or in South America. Okay? So they are special to that region. But for us it is interesting because this kind of a characteristics. So next. So these plants, actually in these regions, UV component in the sunlight is very high. You must remember that in such mountains. So these flowers actually have very fine hair like as well as the leaves. Next. So these actually look completely white. Even the leaves surrounding the petals, they are white. Why is that? So when scientists observed these white hairs, okay, under a scanning electron microscope, they saw that there are filaments of the thickness or the diameter of these thin filaments are about 100 to 200 nanometer, and because of these length scales, they absorb UV light and reflect all other colors. When you reflect all other colors with what you see is white. White light comes, reflects. So these are also these nanostructured filaments that are on this Edelweiss flower are also photonic crystals. and they also actually behave like the way they are behaving because of brand reflection. So what can we do with this kind of technology? We can actually, develop creams or lotions or anything that you can apply on your skin so that you do not get the harmful effects of the UV light. But it will not pass it on to your skin. So also you can have such coatings on cars or any such areas that get deteriorated because of the long exposure of UV light. One can think of such products. Okay, so I spoke about nanostructures, but I just want to know, so what? Why these nanostructures are so special compared to bulk materials that you can see? Why is it so special? In order for you to understand this, I am just giving a cartoon. So you see that there is a cube, okay? There is a cube and whose surface area is 60,000 centimeters square, volume is 10 to the power of 6 centimeter cube, and when you take the ratio of surface area to volume, the value you get is 0.06 per centimeter, very small number. Now you reduce the size of the cube. Go to the next one. The last one has the surface area reduced to 6 centimeters square. Volume is only 1 centimeter cube. But the ratio, look at the ratio. Surface area to volume. It increases by orders of magnitude. It becomes 6 per centimeter. So you have a large surface area on the nanostructures. They may be small. Compared to the bulk material, they may be tiny. But the surface area to volume ratio is much higher compared to bulk material. And this gives them that special advantage. You can do many reactions on these surfaces. You can modify things on these surfaces. And you can make them work the way you want. You can change and enhance their properties, whether it is a thermal property or a mechanical property, optical property, magnetic property. All these things can be enhanced with the nanomaterials, and that's the speciality, and that's what you can do with these materials, and that's what the nature has already told us. It's possible. Okay? So to summarize, the different nature-inspired technologies from the magnetotactic bacteria, you can think of making nanobumpers, and from the diatoms, the microalgae, you can think about making solar cells that work on even on cloudy days. And the gecko has this nanostructure which has inspired the companies to make adhesives and sticky robots. And the butterfly wings and the Edelweiss flower, because of their structural colors, have inspired us to make the technologies that will, stop the fake currency making as well as, the UV protection formulations respectively. So, going to the next slide. Okay, so until now I was talking about the nature-inspired things. So I just want to tell you that I basically work on soft materials. I'm just deviating a little bit. So in the laboratory, I can actually do or make some materials which has nanostructures also in them. This particular material called blue phase liquid crystal actually behave like butterfly wings. They show structural colors. These are not nature, this is in the laboratory. So the next slide, just to tell you what is a liquid. How many of you know what is a liquid crystal? Have you heard about liquid crystal, anybody? If you have, then please raise your hand. Yes? No. Okay, by that. No. Mercury. So the liquid crystal, nobody knows. So that means I must tell you, our Center for Nano and Soft Matter Sciences, we do research both on nanomaterials, nanotechnology, and soft materials, and the technology related to soft materials, and also a combination of these two. So I must tell you what is a liquid crystal, which is a soft material. So next, the liquid crystal is an intermediate state between a liquid and a crystal. So it can flow like a liquid, but it also has some order in them, because of which they show, like the crystal, they show double flash. Okay? So next. And these are organic materials. Next. So there is one liquid crystal which is a very simple type of liquid crystal known as pneumatic liquid crystal. You may be a very liquid crystal itself you haven't heard. It is impossible that you heard this name, but definitely you have seen devices which use this liquid crystal and function. I will show you. You will be surprised. Next. Do you see what is there on the screen? Last, what is there on the screen? I'm sorry, one second. I am asking what is this? A TV. Yes? You have heard about LCD TV? LCD monitor, have you heard? Do you know your mobiles? You all are using mobiles. I don't think there is one person here without mobile. I'm 100% sure. Or 200% sure. All of you are using mobile screen. Mobile. It has a screen, no? It has a screen or no? Yes. So the materials that are inside the screen is a liquid crystal. LCD. LCD means liquid crystal display. Okay. So next time when you see this TV screen or monitor or your mobile, remember that there is a material which flows like a liquid, but still acts like a crystal inside. It is actually embedded between two glass plates inside. Okay, so that is the. So I work on such materials, and I work on a very special material called liquid crystal. Why is it called blue phase? Like I said, these materials, they reflect colors. But the very first time when these liquid crystals were invented, the first person that observed this liquid crystal saw blue light coming in. So he just called it as blue phase liquid crystal. But they can show different colors as well. Next slide. Next. So they act like a butterfly wing. You can see here that this is green and then going to somewhat orange, dark orange, red. So they can show different colors. How they show different colors? I can change the temperature of this material and change the color. I can apply electric field to this material and change the color. So I can do all these things to this material. But with butterfly wings you can't do, right? It can show whatever its color, that's all. I can do this. Next slide. So by doing that, you can see that this first one is red in color. I can increase the voltage, electric field, and make it green. And then I can increase the voltage even further and make it completely colorless. It becomes transparent. So all this is happening because these are structural colors and this material has nano structures in them. And the most interesting thing is that I can change the colors, I can make a device out of it which can change from red to green to transparent. It acts like a smart window. Okay? So the next. So I think I have come to the final slide of my presentation. So I want to tell you a few things. It is not a conclusion. I am not concluding here. I am just giving you some take-home messages. Okay? First, nature is the world's greatest nanotechnologist. We have to be humble. In front of the nature, we have to be humble and acknowledge nature is the greatest nanotechnologist. And learn from nature to solve human problems. In fact, this is an area of research and technology by itself. Okay, R&D by itself. And it is called as biomimicry. Biomimicry. It is an interface between physics, chemistry and biology. It's a biomimicry that you learn something from nature, adapt and create your own products, innovations. You learn from magnetotactic bacteria, the gecko, butterfly, edelweiss, the diatoms and so on. You learn many things. And there are many more examples. I cannot give all the examples here. There are many more. You can look up in the internet. Look at biomimicry, that is a word you can use. Biomimicry, and you will find lots and lots of examples. And finally, next, go back. I just want you to observe the nature, learn from the nature, and innovate. Thank you. Now, if you have any questions, I am happy to take.
Thank you, ma'am, for your wonderful presentation and informative. If you have any doubts, any questions?